All right, how are all of you guys doing this afternoon?
I'm doing well.
Good deal. So today, actually, before we begin today's lecture, I want to point out I set up the web work. Um, all 24 of the homework assignments are available to you all now. And as was discussed when we were talking about the syllabus, the homework assignments are due the day after the following class meeting at midnight. Except for one homework set, because that would have made a homework due on Independence Day, which is a holiday and the university is closed. So that particular homework set's due date got pushed back one day. So there isn't a single instance where you will have homework sets due back to back. So I just wanted to make you guys aware of this. But like I said, everything is up. Lecture videos from previous quarters and all of that kind of stuff are up. So I don't really foresee any reason why having two homeworks due one day after the next at one time will really be particularly prohibitive. All right. Um, so today we are going to be talking about basic electrical quantities. So we are going to be describing and defining in a large amount of detail the different types of signals that we're going to be dealing with throughout this entire class. So we're going to talk about voltage, current, charge, power, and energy, and how all of those quantities are related to each other. And then we'll also be looking at a few examples. All right, so let's start by talking about voltage, because that's probably the concept that you guys are most familiar with. Okay. So mathematically, voltage is defined as follows. So we're going to say that VAB is equal to the line integral from point B to point A of the electric field vector E dotted into some differential line element dl. Now, I fully understand that the overwhelming majority of you all have not yet taken Physics 202, and so you're probably not particularly familiar with electromagnetic field theory. And you will not need to be familiar with electromagnetic field theory in this course practically at all. I am going to bring it up a couple of times, this being one of them, as is necessary to define things, but we are really going to talk our way through things, okay? So this is our mathematical definition of voltage, which we're actually literally never going to use in this class. But if we manipulate this expression just a little bit, we can actually come up with two different definitions for voltage that we will use very regularly. Okay. So let's take a look at the electric field vector E here really quickly. Okay. So there's another relationship, again from electromagnetic field theory, which is known as Coulomb's law. And Coulomb's law is all about the force that acts on a charged particle. So this is an electrical force, so F sub E is equal to Q, the charge of an electron or a proton, times our electric field vector E. Okay. If we substitute in our Coulomb's law relationship into our voltage relationship, what we wind up getting is that the voltage is simply 1 divided by the charge of an electron multiplied by the integral from some point B to some point A of our force vector dotted into a differential line element dl. Now, hopefully, a lot of you guys are familiar with the integral of force dotted into some line element, right? So if I have any mechanical engineers or anything like that paying attention, what is force times distance, or what is the integral of force times distance?
Moment, I guess. Force times distance.
So maybe
Or work done.
work. That's exactly what I'm looking for. So this bit right here is nothing more than mechanical work. And then we're multiplying it by a factor of 1 over charge. So that's going to give us our first definition for voltage. Okay. So we can say that voltage is nothing more than the work per unit charge, because we have that 1 over Q, required to move 1 coulomb, which is the unit of charge, from point B to point A in a circuit. Okay. So this is telling us actually 2 things. Okay. So the first is that in order for charge to move in a circuit in general, there needs to be a voltage somewhere in that circuit. So voltage is what is called an electromotive force, meaning that it provides the push to cause electrons to move around in a path. Okay. So without a voltage somewhere in our system, the net movement of our electrons or charge carriers would be 0. So a voltage is required in order for us to establish what we're going to call a current, which is just the rate at which electrons or charge carriers move. Okay. Now, it also tells us that a voltage is the work done moving charge from point A to point B. So in some materials, it's much, much harder to move charge from one point to another point. And in some materials, it's very easy. And so we'll see that when it's very, very hard to move charge from one point to another, we get very large voltages. And when it's very, very easy to move charge from one point to another, we're going to see very small voltages. We're going to tie this into the concept of resistance in our class meeting on Monday. Okay. So having a voltage somewhere in our system is fundamental to having a circuit work, okay, or behave the way that we would expect it to behave. Now, our second definition for voltage, and this is the one that we are going to use most often, is actually coming about because we have a line integral, right? So a line integral, particularly when we have a conservative force, like the electrostatic force, can be thought of as simply the value at the endpoints of the integral. So this would be VA minus VB, okay? And so this gives us our second definition for voltage. Voltage will be considered to be the difference in electrical potential energy between 2 points in a circuit. And this is the definition that we are going to use the most. So we may not be particularly familiar with electrical potential energy as of yet. However, I feel pretty strongly that we all have a relatively good understanding of what gravitational potential energy is, right? So gravitational potential energy, which you guys should have learned in your high school physics class, as well as your Physics 201, which is a prerequisite for this course for some strange reason, but that's another thing, effectively says, so if we have a surface and we want to lift an object up some height h, then it has a potential energy, which I'm going to call U, of the mass of the object times the acceleration due to gravity times that height difference. So without that height or that distance between the 2 points, we don't have any gravitational potential energy. We see the same type of thing in an electrical circuit. So unless we move far away from some reference point or reference potential energy, which we typically call ground in electrical systems, we don't see voltage drops, right? So we need to have some potential difference relative or with respect to ground in order to have a voltage. And we are going to use this definition very, very frequently. All right. So before we move along from voltage as a concept, does anybody have any questions, comments, or concerns? All right, well, I just thought of something that I probably should have mentioned. Let's talk about the units of voltage. I'll put them over here, right? So in our first definition for voltage, we are told that voltage is the work done per unit charge. What's the unit of work in your physics classes and all of that kind of good stuff? The unit of energy.
Newton meter.
To me, a Newton meter is, I think, torque.
It's Newton.
So Newton is force.
Is it joules?
Joules. That's the unit typically associated with energy, at least back when I was taking physics classes and all of that kind of good stuff. So we're going to have 1 joule per 1 coulomb. So that's work per charge. And we call that a volt, which will have a symbol V. Okay. So that's our unit of voltage. You guys should all be familiar with that as a unit because you've seen it before in your other classes. But this definition is where it comes from. Okay. All right. So now let's talk about representing voltages. Okay. So there are 3 main ways that this is typically done. Okay. The first way that we are going to talk about is what I'm going to call the American way of representing a voltage. So let's say that we have a generic circuit element A, like so. Once again, this is just a simple 2-terminal circuit element like we were dealing with in class on Wednesday could be representative of a resistor, capacitor, inductor, voltage source, current source. We don't really know yet, nor do we really care yet. This is just a general representation, okay? So in the American style of representing voltages, typically speaking, our voltage has a magnitude. So I'm going to represent that here as VA. And just for the sake of argument, I'm going to call this 5 volts. Okay. We also need to include polarity. So I've put a positive polarity sign on top. So we would say that the top terminal is the positive polarity terminal and the negative sign on bottom. So the bottom terminal of element A is the negative polarity terminal. And all this polarity sign means is that the 5 volts drop across this element A. Effectively, the voltage at the positive polarity terminal is 5 volts higher than whatever the voltage is at the negative polarity terminal. So if we had 0 volts down here, we must have 5 volts up here. If we had 3 volts down here, we must have 8 volts up here, etc. Doesn't particularly matter what the voltages at the terminals are. We just know that there is a 5 volt potential difference between those terminals. Again, going back to that second definition of voltage, where a voltage is just the potential difference between 2 points. Okay. Now, if I were to flip the polarity of our terminals, what would the voltage drop across element A be now?
5.
So now it's going to be negative 5 volts. So think about it in this way. How many of you guys, when you used your multimeters in engineering 120 series, accidentally measured a negative voltage? Probably most of you did at some point or another. Well, the way that you got rid of that negative sign was by switching the leads on your multimeter, which is literally physically changing the polarity of your measurement instrument in order to fix things, okay? So if we have 5 volts with positive polarity on top, that is the exact same thing as negative 5 volts with positive polarity on bottom. So if we ever get to a point where we have a voltage that is negative and we don't want to represent it as a negative voltage, we can simply change the polarities of our terminals to get rid of that negative sign. Okay. So this is the American representation, as I mentioned previously. Before we move along to the European representation, does anybody have any questions? All right. So I'm showing you guys the European representation, even though it personally bothers me greatly, because I fully understand that sometimes you guys are going to choose to supplement my lectures with watching videos online and all of that kind of good stuff. And unfortunately, the overwhelming majority of content creators, as it were, in technical fields are not American. And so they typically wind up using the European convention. Okay? So in the European convention, we still have our magnitude of 5 volts, but you'll typically see this represented by, I'm going to do this in a different color because the line's going to wind up going through it, an arrow. Typically speaking, it is a curved arrow, and the head of the arrow represents the positive polarity terminal, and the tail of the arrow represents the negative polarity terminal. So this is just the European way of representing positive polarity on top, negative polarity on bottom, just like we did, just like we did with the plus and minus sign in the American representation. Exact same information, just presented in a slightly different way. I personally don't care for the European representation because I generally associate currents with arrows and voltages with plus and minus signs. It's just what I was used to, or what I am used to. It's how I was taught. I just want to make sure that you guys are aware of the other way to represent things, just in case you happen to watch a video from a creator that is outside of the US, because they may show you voltages in this way. And then the last way that we will see voltages represented is what I'm going to call the double subscript notation. Representation. So we have our generic circuit element. I can call it circuit element A if I choose to. And in this method, our terminals are given specific names. So we have terminal A on top and terminal B on bottom. So we might choose to say that the voltage VAB is equal to 5 volts, where the first letter in the subscript corresponds to the positive polarity terminal, and the second letter in the subscript corresponds to the negative polarity terminal. So this is once again just a slightly different way of representing the exact same information that we see in the American representation. Typically speaking, we don't have to use plus and minus signs to designate the positive and negative polarity terminals, because the order of the subscripts explicitly tells us which is the positive polarity terminal and which is the negative polarity terminal. So if we wanted VBA, this would be negative 5 volts, because changing the order of the subscripts is the exact same thing as changing the polarities of our voltage. Okay. So these are the 3 different ways that we might see voltages represented in a circuit or on a schematic diagram. In this class, 95 or more % of the time will be the American representation, but every now and then, particularly when we get to nodal analysis and maybe a couple other things, we might see the double subscript notation used as well. All right, so before we move along from this kind of mini topic, does anybody have any questions regarding how we represent voltages in a circuit?
I'm not sure if this is a particularly relevant question, but why do they notate the negative with the tail of the arrow and the positive with the head?
I have no idea. If I had to guess, it would be, I was going to say something about maybe dealing with voltage rises and voltage drops, but that's a terminology that I am particularly not a fan of, because I find it arbitrarily I find it confusing. The only thing I could really think of would be it takes 5 volts of potential to move from the bottom polarity or the bottom terminal to the top terminal. And similarly, it would, so that's why the arrow is in that particular direction. But I'm honestly not sure. Any other questions? All right. Now, let's talk about voltage sources. Okay. So there are lots of different types of voltage sources that we are going to see throughout the duration of this course. I think there are 5 different ones that we might wind up dealing with. And so I'm going to talk about all 5 of them here briefly and tell you kind of what the differences are between them, what the similarities are, all of that kind of good stuff. So the first one that I'm going to draw here is a battery. And so this is a symbol that you guys have probably seen very often in your engineering 121 and 122 classes. You might have seen it with only 2 horizontal lines. Typically this symbol, or technically this symbol is representative of a multi-cell battery or a battery pack like you guys dealt with. And if you only have the 2 horizontal lines, that is the technical symbol for a single cell battery. So like a single AA battery or a 9-volt battery or something like that. But they get used fairly interchangeably, so it doesn't particularly matter. The long horizontal line is associated with the positive polarity terminal of the voltage source, and the short horizontal line is associated with the negative polarity terminal of the voltage source. And then our voltage source will have some particular magnitude, and because a battery is a source of DC voltage, I'm just going to choose to represent that magnitude with a symbol here, VDC for right now. Okay. So this is our first representation. Our second voltage source that we might see is a generic DC voltage source. This is the one that I use significantly more often than the battery symbol. It's a circle, and then the positive polarity terminal is the terminal that's denoted by the plus sign. The negative polarity terminal is the terminal denoted by the minus sign. And this is also an example of a DC voltage source. So it's going to have a similar magnitude representation. So this is our generic. That C looks too much like an E for me. So this generic DC voltage source and the battery are presenting, once again, the exact same information, just in a slightly different way. I prefer the generic DC voltage source as a way to represent a DC voltage source as opposed to the battery symbol, because in a couple of weeks, we're going to introduce the capacitor. And the schematic diagram symbol for a capacitor is effectively 2 parallel lines. And it can be easily confused with the symbol for a battery if you are doing things hastily and not paying attention. So there's no ambiguity whatsoever with the generic DC voltage source being confused with some other circuit element, which is why I personally prefer. Next, we are going to have our generic AC voltage source. And so this is going to be almost the exact same thing as our generic DC voltage source, except that I'm going to put this little tilde in the middle, which lets us know that the voltage is varying in time. So we might see this its magnitude effectively represented as VAC. These are all lowercase letters as a function of time. So one thing that I want to point out here, whenever I write a symbol in capital letters, that typically means that it is a DC quantity. And whenever I write a symbol in lowercase letters, that typically means that it is an AC or time varying quantity. I won't always adhere to that, but I will try to. In the web work assignments in particular, there's a lot of times where they represent AC quantities as capital letters and other times where they represent DC quantities as lowercase letters. At some point, I will find the time to go through and fix that, but I haven't done it yet. All right, so before we move along to the other two or the last two voltage sources that we're going to see in this class, I want to point something out. So these three voltage sources are what are known as independent sources. So an independent source simply means that these voltage sources provide a fixed amount of voltage regardless of what they are connected to, okay? So if we have a 5-volt battery, it is providing 5 volts of voltage regardless of if it is connected to nothing or a combination of resistors, capacitors, inductors, etc. Okay, so we are going to treat all of these independent sources as effectively ideal sources, meaning that they don't care what they are connected to at all. To contrast that, over here on the right-hand side, I'm going to show you dependent sources. So we're going to have two different types of dependent voltage source, and their symbols are literally identical. Okay. So these dependent sources are going to be represented with a rhombus or a diamond shape as opposed to the circular shape used for the independent sources, at least the generic independent sources. Okay. So first, let's talk about a voltage controlled voltage source. And then over here on the right, we will have a current controlled voltage source. And I will typically refer to these by their initials. So this would be a VC, VS, and this would be a CC, VS. Now, as you guys can see, the symbols for these two different types of dependent sources are literally the exact same thing. So the only way to differentiate between the two of them is by looking at how the magnitude of these voltage sources is represented. So in a voltage controlled voltage source, we will typically see K, where K is just an arbitrary constant having units of volts per volts. By the way, these units may not be given to you, but volts per volts is effectively a unitless quantity. And then that scaling factor K will be multiplied by some controlling voltage, which I'm choosing to represent here as a voltage Vx. So the amount of voltage that is provided by this voltage controlled voltage source depends on the voltage Vx, which is located elsewhere in the circuit. Typically, voltage controlled voltage sources and current controlled voltage sources are used to represent more complex pieces of electronic devices like amplifiers and things like that. We are just going to use them as kind of a generic tool in this class, but for those of you that are in electrical engineering, we will use these in mathematical models for complex circuits very, very regularly. So we can see that this one is a voltage controlled voltage source because the controlling variable is a voltage, Vx. For our current controlled voltage source, we are going to have some scaling coefficient, which I'm going to choose to call lowercase r, and it will have units of volts per amp. And then our controlling current, I'm going to call it IX. So I want to be very clear here because this is a point of confusion, particularly early on in circuits 1. Even though this current controlled voltage source is dependent on some current somewhere in the circuit, it is outputting a voltage. We can see that very easily by looking at the units, right? So we have volts per amp. You guys hopefully remember that the units of current is the ampere or amp. So volts per amp times amps gives us a voltage, okay? So even though this depends on a current, it is indeed a voltage source. And we can tell that it is a voltage source by looking at it because it has a clearly defined positive polarity terminal and negative polarity terminal. Hopefully that wasn't too confusing of a spiel. All right, so these are our dependent sources. And they're called dependent sources because their value depends on some quantity elsewhere in the circuit. It's perfectly reasonable for you guys to be a little bit confused right now, particularly with the dependent sources. Hopefully we will sort that out as we work example problems and all of that kind of stuff throughout the duration of the class. One thing that I want to make explicitly clear here, I will not always remember to tell you what the units of the scaling factor for these dependent sources is. I try to do a pretty good job of it. That being said, most textbooks and all of that kind of stuff put no effort into making sure that the units make sense. So I've told you very explicitly that when we have a voltage controlled voltage source, the scaling factor K has a unit of volts per volt. When we have a current controlled voltage source, the scaling factor of R will have units of volts per amp unless otherwise stated. Okay, so sometimes it might be volts per milliamp, etc. But if you're not told anything, assume that these are the units that you should use. All right, I've talked for the better part of 40 minutes about voltage. So does anybody have any questions about voltages before we move on to currents? All righty. So mathematically, current is defined to be the derivative of charge Q with respect to time. Where charge, as I've mentioned before, is measured in coulombs. So that means our units for current would be 1 coulomb per 1 second, which we commonly refer to as an ampere, which has a symbol of A. Okay. We can mathematically manipulate this relationship. So here we have current, which depends on charge. Well, if we know current and want to find charge, we can simply say that charge Q is equal to the integral of our current And I'm going to do something a little bit weird here, and I'll explain it in just a moment. I'm using a dummy variable here, t prime, that is representing time, okay? So the reason why I'm using a dummy variable t prime is because I have t time in the limits of my integration, and it would be confusing if I used t in both places. I will never ask you to perform a derivative operation in this class by using a prime notation like you might have seen in your math classes. So prime here in circuits literally never, ever, ever means take a derivative. I just want to be really, really clear about that. We're going to add to this thing Q at some point in time T naught. This is what we're going to call an initial condition. So in order for us to be able to determine the amount of charge that is past a certain point in our circuit, based on the amount of current that's flowing in our circuit, we need to know what the charge was doing at some point in time, which I generically call T naught. Okay. I want to be very explicitly clear here that this bit is not inside the integral. Okay. So we're integrating our current, and then we're just adding some constant value to that, representing what our prior knowledge about the system was. All right. So there's our mathematical definition for current, and then we kind of inversed that mathematical definition to get us a mathematical definition for charge. Now let's use a definition or come up with a definition that's just using words that might be a little bit more helpful, at least with understanding what's going on. So current will be defined to be the rate at which charge passes a certain point in a circuit. And this is the same thing as the rate at which charge flows through a circuit element. Do I need to go into further detail about what currents are in a circuit? Like, do I need to hit you guys with some physics, or are you good? I will assume from the lack of response that you're good. Okay. So now let's talk about how we represent currents in a circuit. And luckily for us, there's pretty much only one way to do this. Okay? Or at least we're only going to see one way in this class. So if I have my generic circuit element A, and let's say that there is a magnitude of 2 amps of current flowing in this circuit element. So we could say that IA is 2 amps. We describe the magnitude with a number in order to have a complete definition for current. We also need to indicate a direction. So I'm going to choose to say that there is 2 amps of current flowing down through this element. So flowing from the top terminal to the bottom terminal, we see 2 amps. So if I wanted to know how much current is flowing up, so from the bottom terminal to the top terminal, how might we quantify that?
Do the same as we did with voltage and just do a -2 amps.
Exactly right. It literally doesn't need to be any harder than that whatsoever. So 2 amps flowing down is the exact same thing as -2 amps flowing up. So much like we saw with voltages, whenever we have a negative sign here for a current, in order to get rid of the negative sign, we simply change the direction of the current, just like we change the polarity of the voltages. Okay, so fantastic job. Like I said a couple of moments ago, this is really the only way that we're ever going to see currents represented in this class. In other electrical engineering courses, higher level ones, we have a double subscript notation as well, but we don't really need to get into that here since we won't see it. All right, so let's talk about current sources. So first one that I want to show you guys is the generic DC current source. So we have a circle like we've had for our other generic sources. And there is an arrow in the middle of the circle indicating the direction that current is flowing. So I'm going to choose to represent the magnitude of this current with a capital I DC because it's DC current. We might, or much later on in the class, we will also see AC current sources. It's going to be the exact same symbol, except that I'm going to put that little squiggle or tilde in the middle of it to let us know that this current is changing in time. So this will be lowercase I AC as a function of time. And this is our generic AC current source symbol. And these are our independent current sources. We are also going to have 2 different dependent current sources, much like we had for our voltage sources. Very similar symbol. So we have a rhombus or a diamond shape letting us know that we have a dependent source. And now we're going to have an arrow, which is letting us know that that's a current source. Over here, let's take care of the current controlled current source first. CCCS. And over here on the right, we will have a voltage controlled current source, or VCCS. Okay. So in a current controlled current source, we're going to have a scaling factor of K. This time our units are going to be amps per amp or unitless. And then we are going to have a controlling current of IX. And then for our voltage controlled current source, our scaling factor, I'm going to give it a symbol of lowercase g. And it will have units of amps per volt. And then our controlling voltage will be given the symbol of Vx.
For that current control, that's amps per amp, correct?
That is indeed amps per amp. Let me rewrite that because apparently my penmanship got terrible there. Amps per amp. Is that clearer to read?
Yes, sir, that's good. Thank you.
And I'll fix this one to look more clear as amps per volt. Sorry about that.
Okay.
All right. So we've talked about what current is. I remembered to give you guys the unit. We talked about how we're going to represent currents on our schematic diagrams. And I've introduced the different types of current sources. Before we move on, I want to ask you guys maybe a weird question. So I feel pretty strongly that you guys have a good grasp of what a voltage source is because every single one of you at some point has held a battery in your hand. How many of you have any experience with a current source? So realistically, the answer is probably 0 or very close to 0. Current sources are very much a piece of equipment that you can purchase, but typically speaking, they are very expensive and they're used in laboratory settings. Current sources are used to represent complicated transistor-based circuits, which are used to provide bias currents to sensitive electronic devices. So that's where we'll practically see current sources, would be later on in higher level electrical engineering classes. But as a concept, we will play around with them quite a bit here in Engineering 221. But it's not anything that you'll ever really physically interact with in this class. So I just wanted to point that out. All right, any questions regarding current? All righty. So now let's talk about power and energy. So let's start by looking at power. And I'm going to define this as if power is a time varying quantity, which it could be, but if we have DC power, we can just literally throw away all of the time dependence and still be perfectly okay. So the definition that you guys are probably most familiar with for power would be that power is the product of voltage and current. And there is nothing remotely wrong with that representation whatsoever. In fact, we are going to use it a whole heck of a lot in this class. However, we can look at things in a slightly different way. So we know that current is the derivative of charge with respect to time. And we know that voltage is equal to the integral of effectively energy with respect to time multiplied by charge. So we could actually rearrange that voltage relationship as the derivative of energy with respect to charge and we can see, and I'm sure if we have any math minors in here, they're going to absolutely hate this, that the dq terms cancel out. And so we're left with just the derivative of energy, W, with respect to time. So power has units of joules per second, which we commonly refer to as a watt, the symbol capital W. Okay. And our word-based definition for power is then going to be the rate at which energy is transferred in a circuit. Now, this is a little bit of circular reasoning here, and I apologize for that, but in a circuit theory class, energy, W, is defined as the integral of power. Typically, energy is determined over some fixed interval of time. So I'm just going to represent that by some time t1 up to some time t2, where the unit of energy is the joule, which we've talked about previously. And our word-based definition is the total amount of power transferred in a fixed amount of time. So our definitions for power and energy are literally tied to each other. They just represent the rate at which a transfer of energy is happening or the amount of power that is transferred in a fixed amount of time. It's kind of, they're not interchangeable, but they're pretty darn close. Okay. So I want to talk now about what's called the passive sign convention. It's specifically related to power and energy. And for whatever reason, and I genuinely don't know why, this is one of the most difficult concepts to grasp in this class. Okay. I'm going to try to explain it to you. I'm more than happy to entertain questions about it throughout the duration of this course, but I want to be rather clear about this. This is something that you will be effectively tested on in every single homework assignment, every single exam, all of that kind of stuff throughout the duration of the course. So not getting a good handle on this concept can literally be the difference between a letter grade or two in this class. So just trying to give you guys fair warning. Okay. All right, so passive sign convention. So in a nutshell, all the passive sign convention actually means is that whenever something is happening to an element, it gets a plus sign. And whenever something is happening because of an element, it gets a minus sign. We're going to go into a little bit more rigorous detail about that here in just a second, but that's really all that the passive sign convention means. Okay. So let's consider a generic circuit element A. Okay. And I've drawn some long terminals like this so we can really see what's going on. Okay. So I'm going to put some ellipses here. And all these mean is that this element A is connected as part of some larger circuit that we don't really know anything about or care anything about at this point. Okay. All right. So I'm going to define a voltage drop across the terminals of element A. And I'm going to call it VA like this, positive polarity on top, negative polarity on bottom. And then I'm going to define a current that's flowing through element A. And in this case, I'm going to define the current as flowing into the positive polarity terminal. Okay. So the passive sign convention tells us that when the current is flowing into the positive polarity terminal, the power absorbed by element A is simply VA times IA. I'm going to put a note out here. Absorbed, or negative VA times IA for supplied power. So the difference between absorbed power and supplied power is simply a factor of -1. So if we have something that is absorbing 5 watts of power, it is supplying -5 watts of power. Okay. So anytime the current is flowing into the positive polarity terminal of a circuit element, the product of voltage and current is the absorbed power. In contrast, let's put an element B over here to the right. It's part of some larger circuit. We will define the voltage drop across element B to be VB. And I'm going to say that there is a current of IB. And this time the current is flowing into the negative polarity terminal. So for this case, we are going to say that the product of voltage and current is the supplied power. And therefore, sorry, that should be, all of these subscripts should be B. My apologies. And our absorbed power is simply the negative of our supplied power. Now, I want to point something out here. At no point did I specify whether my voltage VA or my current IA, my voltage VB or my current IB, I never specified whether those were positive or negative quantities because it literally doesn't matter at all. Whenever current is flowing into the positive polarity terminal, the product of I and V is absorbed power. Whenever current is flowing into the negative polarity terminal, the product of current and voltage is supplied power. And then we can use the sign on that calculated power to tell us whether or not it's actually supplied or absorbed. This is all the passive sign convention needs to be. This is as difficult as it gets with regards to this concept, and we are over time going to practice this so much that it should become completely and utterly rote. Okay. All right, one last thing, and then we'll work the in-class assignment. So this is going to be what's called Teligens's theorem. So Teligens's theorem states that the sum of the absorbed powers and supplied powers in a system must equal to 0. Okay? So Teligens's theorem is nothing more than a form of the law of conservation of energy as applied to circuits. It actually isn't the only one. In our next class meeting, we're going to talk about Kirchhoff's voltage law, which is the more common representation of the law of conservation of energy in circuits, because having a voltage drop literally means that we have to transfer energy or perform work to move charge around. So it's kind of the same thing. So this is just kind of a sanity check rule. If we calculate all of our absorbed powers and all of our supplied powers, add everything together, and it doesn't equal 0, then we've made a mistake somewhere. So this is just a way for us to check things. All right, so as far as all of the theory and all of that kind of good stuff goes, we are done for the day. Does anybody have any questions before we start looking at the in-class assignment?
So for your element A in this example, if, for example, you flip the polarity on the VA, would these two equations would still be the same? You would just have another negative in there.
So if we flipped the positive polarity terminal on element A to be on bottom, our current IA would then be flowing into the negative polarity terminal, right? So that would be the same thing as effectively us putting a negative sign here and another negative sign here, which would flip this one to positive. And I'll be damned if it doesn't give us the exact same relationship as we have on the right-hand side, because we have the same thing. The current's flowing into the negative polarity terminal. Does that make sense?
Yes, sir.
All right, so because I'm dealing with a new computer, I don't know that I have the in-class assignments actually saved on here really quickly, so I'm pulling them up on my desktop, and I'll write things out. Give me just a moment, sorry about this. All right, so problem number 1 for our in-class assignment says the charge entering, sorry, I can't spell, the positive polarity terminal of a particular circuit element is given by the equation Q of t is equal to IMT plus QM sine omega t, where IM is equal to 6.3 milliamps, QM is equal to 2.1 millicoulombs, and omega is equal to 1.3 radians per second. We are asked to determine what amount of charge enters the circuit element at t is equal to 700 milliseconds, and B, what amount of current flows through the circuit element at t is equal to 700 milliseconds. Sorry, my hand is getting tired, and so my penmanship is worse than normal. If anything isn't clear, please let me know. All right, so I think, or at least I hope, that it is fairly obvious that this question is testing our knowledge of the relationships between charge and current. Okay, so that's where all of the equations that we're going to wind up using are coming from. So for part A, what amount of charge enters the circuit element at t is equal to 700 milliseconds? How do you think we're going to approach that?
I would assume just plug everything into the Q of t equation.
Exactly right. We have an equation for charge, and we're trying to find charge, so why would we need to do literally anything else? So 100% correct, Baylor, thank you. So for part A, Q at 700 milliseconds. So I'm going to call 700 milliseconds 0.7 seconds because those units will work out better for me. So Q at 0.7 seconds is going to be IM, so that is 6.3 milliamps times 0.7 seconds plus QM, so 2.1 millicoulombs times the sine of omega, so 1.3 radians per second times t of 0.7 seconds, like so. So let's play around with the units here really quickly, right? So we have 6.3 milliamps. So if an ampere is a coulomb per second, based on what we talked about earlier, then a milliampere is a millicoulomb per second times 0.7 seconds. We can see very easily that the seconds cancel each other out, and we're getting a charge measured in millicoulombs. Over here, we have 2.1 millicoulombs times the sine, so 1.3 radians per second times 0.7 seconds. Once again, we have seconds canceling seconds. So I want you guys to throw this in your calculator and tell me what you get.
$6.068.
Did anybody get anything different than that? Like perhaps 4.443.
For just a second term, I got 4.41, if that's what you're asking.
I got a full answer of 4.443.
Okay, so I was expecting somebody to get an answer of 4.443. The correct answer is the 6.068 millicoulombs that is given on the assignment sheet. But that 4.443 answer seems like it should be correct. However, I can pinpoint exactly what the problem is. Okay, so I want you to notice here, we're taking the sine of 1.3 radians per second times 0.7 seconds. So whenever we have an angular frequency expressed in radians per second, and we multiply it by time expressed in seconds, we get an angle that is in radians. I would be willing to bet that your calculator is set in degree mode, which is
Yes,
why you're
sir.
getting the wrong answer.
Yeah, I had changed my mode because I saw the radians.
Yep. So I will do my damnedest to make sure that I tell you when things are in radians and when things are in degrees so that you know what mode to set your calculator in. But you do very much need to be paying attention to those kind of things. Okay. So, all right. So 6.068 millicoulombs. All right, so for part B, where we're asked to determine current, how are we going to do that?
Use the 6.068 and isolate for the current.
I may have misheard you, but what do you mean by isolate for the current?
We'll solve for the current.
Okay. Mathematically describe what that process would be, or if you want, I can let you share your screen.
I can't share my screen because I'm doing this on my iPad and computer.
Okay.
So it would be the Q minus, or the Q of T minus Q sub M sine of omega T over T, which would leave you just with I sub M on the right side, then giving us current.
Right, but I sub M,
Oh wait, never mind, because that's given. Never mind.
exactly right. Yep. So go back to your notes, because I feel quite strongly that I gave you guys a relationship that relates charge and current. So we are trying to find current when our charge is well defined. So I believe, sorry, go ahead.
Would you just divide the charge by the time?
That's closer, but still not quite right. So let me scroll back up here. So whenever we're given charge and we want to find current, if our charge varies in time, we need to take the derivative. If our charge didn't vary in time, well, actually, then our current would be zero. But what you're describing is very commonly used to calculate average current. So if we know that on average, a certain amount of charge passes a particular point in a certain amount of time, then it's just, the change in charge divided by the change in time gives us our current. But here explicitly, we're going to need to use the derivative relationship in order for us to get an accurate representation of what the current is doing at t is equal to 700 milliseconds. So scroll back down here to our doing math. So our current at 0.7 seconds is going to be the derivative of Q with respect to time evaluated at t is equal to 0.7 seconds. So how am I going to take the derivative of that expression for charge? So here's our Q of t relationship. You guys are engineering students who are in math 243, 244, all that kind of good stuff at this point, probably. How do I take this derivative?
Well, everything's a constant besides the sign, so it'd be
Mm,
no.
No, you have the Q, you have the IM.
Yeah.
so, okay, so,
IM plus QM omega T sine of omega T.
so is the derivative of sine positive cosine or negative cosine?
Sorry. It's positive cosine.
Okay. So IM plus omega QM cosine omega t, and then this thing evaluated at t is equal to 0.7 seconds. So let's look at how things work out here with the units, right? So IM was given to be 6.3 milliamps. Omega was 1.3 radians per second, where a radian is a dimensionless quantity, so it's not really going to do anything in particular to us. QM was 2.1 millicoulombs. So we have millicoulombs per second plus milliamps. So that's just milliamps plus milliamps. So things look pretty okay to me. Then we have cosine of 1.3 radians per second. Sorry, that got away from me. Times 0.7 seconds. Okay. So I'm going to throw this in my calculator, even though I know the answer is on the sheet. I always like to make sure I didn't make any mistakes. So 6.3 plus 1.3 times 2.1 times the cosine of 1.3 times 0.7. And because my calculator is set in degree modes, I'm going to introduce a conversion factor. That's just going to be pi over 180. Oh, good God, and I did not get the right answer. Maybe I'll just try putting my calculator in radian mode and not being lazy. $7.9755, so 7.976. Milliamps. All right. So problem one taken care of. Any questions, comments, or concerns before we move along to problem two?
With that, with the initial condition, where would that factor in?
So that initial condition relationship would be used to calculate charge if we knew current. So let me see what the next problem is and make sure we're not about to do it. That's power. Nope. All right. So let's work a quick example thing just to illustrate that particular relationship being used. So this isn't one of the in-class assignment problems. It's just something I want to make sure that you guys know how to do. So let's say that our current I of t were 8e to the negative 6t milliamps. And we know that the charge at t is equal to 0 seconds is 20 millicoulombs. And we want to find the charge at 5 seconds. So Q at 5 seconds would be the integral from 0 seconds to 5 seconds of 8e to the negative 6t milliamps dt plus our initial condition of 20 millicoulombs. So that 8 milliamps is a constant, so I can pull that to the outside. What's the integral of e to the negative 6t?
Be negative 1/6 e to the negative 6t.
So e to the negative 6t divided by negative 6. Same thing you said, just expressed in a slightly different way.
Sure.
And then evaluate that at 5 seconds and 0 seconds. Add to this 20 millicoulombs. So that's going to be, let's see, 8 milliamps. E to the negative 30. Sorry, let me move this up quickly. Minus e to the 0, which is just 1, divided by negative 6 plus 20 millicoulombs. And I can throw that in my calculator. So 8 times E, oh crap, wrong button. I got 56 thirds of a millicoulomb. And sorry, one thing I want to point out here, and I'm playing a little fast and loose with the units. So this 6 right here is being multiplied by time t, which I'm assuming is measured in seconds. So this 6 has units of per seconds. So if we put a seconds to the -1 here and a seconds to the -1 here, we have effectively milliamps times seconds, which is the same thing as a millicoulomb, which is what allowed me to add those two quantities together. So I apologize for being a little, or forgetting to include the units there. On a test question or something like that, I would typically actually write this out as 8e to the alpha t, where alpha is equal to -6 per second, so that I was very clear about what the units were. But anyway, that's how we would use that particular relationship. Was that helpful in any way, Baylor?
Yes, sir. Helped a lot.
Alrighty. All right, so let's look at problem 2, unless there were any other questions. All right. So in problem 2, I don't want this to take too long because we only have 20 minutes left of class. So we'll go through this one a little bit more quickly. So our given information is effectively our charge as a function of time is qm e to the negative alpha t, where qm is equal to -30 millicoulombs and alpha is equal to 4 per second. The voltage across the terminals of our element is given by Vm e to the negative beta t, where Vm is equal to 120 volts and beta is equal to 2 per second. Part A wants us to find the power absorbed as a function of time. I'm going to make a note here. And for part B, we want to calculate the energy over the interval 0 is less than t is less than 50 milliseconds. So does anybody have any thoughts? Oh, I put C when that's very obviously B. Anybody have any thoughts about part A of this problem?
Plug it in.
Plug it in. So what are we plugging in?
Your q into your equation q sub m e to the negative of t. You plug in the q sub m in the alpha.
So that's going to give us a charge at a particular point in time. How is that going to help us calculate power?
Take the integral.
Yeah,
I mean, not a meant derivative.
Derivative, absolutely right. So for part A, we know that power can be expressed as voltage times current, which is the same thing as voltage times the derivative of charge with respect to time, right? Because we're looking for a function, I'm just going to leave things in this form, right? So we are going to have Vm e to the negative beta t multiplied by the derivative of qm e to the negative alpha t, which I believe is going to be negative alpha qm e to the negative alpha t. I'm going to lump things together here. So that's going to look to me like negative alpha Vm Qm e to the negative alpha plus beta t. And now I could substitute in my numbers. Because we're pressed for time, I'll leave that up to you guys. But did any of that process not make sense? I will assume your silence means that you agree with me. So how would we do part B?
Would you just take the integral with the 2 times given in part B?
Exactly right. That is 100% it. So our energy would be the integral from 0 to 0.05. So I like to do all of these things in seconds because time is usually measured in seconds, at least when it comes to electrical engineering, of the power equation that we got in part A. Absolutely right. And for the most part, you could literally just throw that in your calculator and have it spit out an answer for you. So we only talked about the process for this one. We didn't really hit it with the numbers, so I'll leave you guys to do that. I want to work through problem 3 all the way, I guess, because it's the one that's dealing with the passive sign convention, and I feel like that's the most confusing thing that we talked about today. So does anybody have any questions about this problem before we move along to problem 3? All righty. So let's look at number 3 really quickly here. So in this problem, we are given a circuit. So I'm going to go ahead and draw this circuit out for you all. So here we have a 36-volt source. And then we have a generic circuit element that I am calling element 1, it looks like. Here we have a generic circuit element that I am calling element 2. We have a dependent source here. This is a dependent voltage source, and it is a current controlled voltage source with a scaling factor of 1. And then over here on the right-hand side, we have a generic element 3. And let me fill in some information. So we're told that the voltage drop across element 1, positive polarity on the left, is 12 volts. We're told that the voltage drop across element 2, positive polarity on top, is 24 volts. We're told that the voltage drop across element 3, positive polarity on top, is 28 volts. The current flowing through element 3 is 2 amps direction down. The current flowing through element 2 is 2 amps direction down. And the current flowing through element 1 is labeled IX. So this is the current that's controlling our dependent source, and it has a magnitude of 4 amps. And we are asked to calculate the power absorbed. I'm going to underline that, by each element. So let's start with element 1. Okay. So what's the voltage drop across element 1?
12 volts.
What's the current flowing through element 1?
4 amps. I don't know if that'd be a positive or negative thing.
So we're going to sort that out here in a second. Okay. So voltage is 12 volts. Current is 4 amps. Now, is the current flowing into the positive polarity terminal or is it flowing into the negative polarity terminal?
It's blowing into the positive.
It's flowing into the positive, and we were asked to calculate absorbed power. So we don't need to add a negative sign. So 48 watts. Now let's look at element 2. Somebody else tell me what the voltage drop across element 2 is.
24 volts.
24 volts. What's the current flowing through element 2?
2 amps.
Is the current flowing into the positive polarity terminal or into the negative polarity terminal?
Into the positive, out of the
Positive.
negative.
Yep, so into the positive because it was flowing out of the negative. Absolutely correct. So once again, because we were asked to calculate absorbed power, we don't need to add a negative sign. So this one is also 48 watts. Element 3, somebody else. What's the voltage drop across element 3?
28.
Thank you. What's the current flowing through element 3?
2 amps.
Is the current flowing into the positive polarity terminal or into the negative polarity terminal?
Into the positive.
So once again, we don't need to change the sign on anything. So 28 times 2 is 56. And there we go. All right. So now let's do our independent source. So that is the 36 volt source. So what's the voltage drop across the 36 volt source?
It
30.
doesn't say. Or
I feel like somebody might have just said it doesn't say. I disagree with that.
36 volts.
It's 36 volts. Absolutely. How much current is flowing through the 36 volt source?
4 amps.
4 amps. Okay. I agree with that. Is that 4 amps of current flowing into the positive polarity terminal or into the negative polarity terminal?
Into the negative.
Negative.
So because it's flowing into the negative polarity terminal and we're calculating absorbed power, we need to add a negative sign. So 36 times 4 times -1 is negative 144 watts. Lastly, we have our dependent source. So P dependent. Okay. So this one is a little bit tricky. What is the voltage drop across our dependent source?
Four volts.
Okay, how did you get that? You're absolutely correct, by the way.
IX is equal to 4 amps, and your conversion rate is 1. So 4 amps times 1 just makes 4 volts.
Exactly right, where that 1 has implied units of volts per amp. So even though it wasn't specified, we know that it is a current controlled voltage source, and therefore the scaling factor has units of volts per amp. Great job. So 4 volts. What is the current flowing through the dependent source?
2 amps.
2 amps. Okay. Is that current flowing into the negative polarity terminal or into the positive polarity terminal?
Into the negative.
into the negative, which means we need to add a negative sign. So that looks to me like -8 watts. So we have all of our absorbed powers. Just as a sanity check, what happens when we add all these numbers together?
Equals 0.
Yep, so 48 plus 48 plus 48, because 56 minus 8 is 48. So that's literally 12 times 12 is equal to -12 times 12. So it looks like 0 to me. So intelligence theorem was satisfied, which means we didn't make any mistakes. Great job. All right, so we fully worked out in-class assignment problem 1 and in-class assignment problem 3. Problem 2, we set everything up. I would encourage you guys to take a crack at, just plugging the numbers in and making sure everything makes sense. As a reminder, the in-class assignments are due before our next class meeting starts. So that'll be Monday at 2 p.m. There is a 5-minute grace period, but I mean, realistically, you should be able to finish it up in the next 5-ish minutes and then go ahead and scan it and submit it. As I mentioned at the top of the class, all of the web works have been assigned. Your first homework set will be due Tuesday at midnight. I am more than happy to answer any questions that you guys may have via email over the weekend. But if you want to save them so that we can discuss them at the beginning of class on Monday, that's perfectly acceptable as well. I hope you guys have a great weekend, and I'll see you on Monday. If you have any questions, I'd be happy to hang out and answer them.
Dr. Hartman, could you just go back to problem 2?
Sure. Would you like me to clarify anything, or did you just want to see it?
I guess I'm just getting stuck on the alpha times VMQME, because then you'd have 120 volts times the -30 millicoulombs,
Mm-hmm.
which would obviously give you more than 14.4. Even if you divided it by 4, they give you like what, 90?
So let's look at things really quick here. Let me do it in blue, right? So we have negative alpha, so -4 per second times our voltage, so 120 volts. And then we have -30 millicoulombs. So -30 times 10 to the -3 coulombs, okay? So we can see, I think pretty easily, that this negative sign and this negative sign are going to cancel each other out. We have 120 times 120. So that is going to be 144, and then should be 2 more zeros. But then we have times 10 to the -3, which is going to put that decimal place right there. And our units are volts times coulombs per second, which is the same as a volt times an amp or a watt.
Right, sorry. I got lost when you said 12 times 12.
Oh, 120. So 4 times 30 is 120. And so 120 times 120 is the same thing as 12 times 12 times 10 times 10, because I am an insane person. And that's how
All right. All right. Okay, I get it now. All right, thank you.
Yeah, sorry, I do math real weird in my head. I apologize for that.
Did the
It's
same.
all right. It's efficient, but I got lost.
Yeah, the 14.4 watts does seem legit.
All right, thank you very much.
Yep, no problem. Sorry for being a weirdo, more than usual.
Dr. Hartman, will you go back to number 3?
Sure.
Whenever you solved for the dependent one, the 2 amps, I'm confused right there. Like I got lost right there.
Okay. So technically speaking, I'm relying on you remembering a little something called Kirchhoff's current law here, which we are not going to formally talk about until Wednesday, but I can explain it pretty easily. So we know that 2 amps is flowing down through element 3 because of this information right here, right?
Okay.
So that means that that same 2 amps has to be flowing through that dependent source because there's nowhere else for that 2 amps to flow.
Okay, I'm following.
Okay, so that's all it was.
Okay, thank you.
No problem.
Think of it like water in a pipe.
You could.
Dr. Hartman, on that same dependent variable, could you re-explain how we knew the voltage was 4 right there?
Sure. So let me write it out over here. So the voltage drop across our dependent source is, we're told it is 1 IX. So I am going to give the units of that 1 as volts per amps, because if we go back to our notes, the scaling factor on a current controlled voltage source should have units of volts per amp. So that is 1 volt per amp times IX, which was given as 4 amps, comes out to be 4 volts.
Yeah, that makes sense. For some reason I saw that and thought element 1 was getting 4 amps and not just IX being 4 amps.
So element 1 is getting 4 amps, but I don't know.
IX also equals 4 amps.
Yep.
All right.
Yeah, so this is our first problem with a dependent source. So these things are going to be a little bit confusing until we just get more practice with them. So like that current IX is effectively fulfilling 2 roles. It is the current that's flowing through element 1. Actually, so generally speaking, I would think of it in the opposite direction. So I would say that, that dependent source is being controlled by the current that's flowing through element 1, and that current happens to be 4 amps. Like that's how I would generally think of things. I don't know if that helps or not, but at least that's my thought process.
That 4 amps that comes out of element 1, that gets evenly split between any elements on the other side of element 1.
So you're effectively asking about Kirchhoff's current law, and you are correct that if 4 amps is flowing into this node, then 4 amps has to flow out of that node as well. And we'll talk about that in much greater detail on Monday.
Okay. I remembered that from 120, I believe.
Yep. Yeah, we'll look at Kirchhoff's current law 3 different ways that are all effectively the same thing on Monday. And then I'll tell you which one I prefer and why I prefer it. But you're welcome to use any of the representations because they're all the same thing. Any other questions before I go walk my dog? Alrighty, well, I hope you guys have a great rest of your weekend. And like I said, if you have any questions, I'd be happy to answer them over email or at the beginning of class on Monday. You guys be safe, and I'll see you next week.
Thank you, Dr. Hartman.
You're very welcome.